and ask me. You can either unmute yourself or go ahead and put it into the chat, but let's get going for the day. And so we kind of learned about scalar multiplication yesterday. We went through the introduction portion of it. And so today we're going to work through the assignment. So remember, when we talk about multiplication of matrices, the scalar is just the number like out in front. It's like the coefficient of the matrix. So in this case, we're talking about, hey, if we have some matrix and we have that coefficient out in front, that number that we're multiplying to everything inside each element inside the matrix. What if this says, what are true? What's true about that idea of scalar multiplication? So again, this isn't multiplying two matrices together. It's strictly talking about the scalar portion of it, of just that coefficient. So the first one says, so again, we're checking the ones that are true, all that apply. So it's not just pick one. So make sure that you don't see the first one and then you just go, oh yeah, I got it, and then submit, because you'd get it wrong. So it says, which of the following statements are true about scalar multiplication of matrices? You can multiply a matrix of any size by a scalar. That is absolutely true. What that means is if I have some matrix, let's say 3, 2, -1, and I multiply by a scalar, some number out in front, some coefficient, some values such as 2. Remember, if it's 2 times this matrix, then it's 2 times every one of these element pieces, and they stay in order. So if I was to multiply that out, then this would be 6, 4, and -2. And I could do that for any size or shape. It could be a 3 by 2, a 5 by 5. It does not matter, but that would be true. For any matrix A, if I do 1 times that matrix, I end up with that matrix. I end up with A. If this was a value 1, I multiplied it to everything, I would still end up with the same matrix. So this is true. For any scalar R, then if I have R times I, it's equal to I, where I is the identity matrix. So it says for any scalar R, so any value of R. So let's say, what if I say R is equal to 2, and I multiply it by my identity matrix? So I'm going to pick one of my identity matrix. Remember, an identity matrix is square. So I'm going to do my I2. I won't label that 2 because I don't want to confuse you guys. So when I say my I2, I'm going to do a 2 by 2. And remember, when we talk about that, the diagonal here has to be 1s, everything else is 0s. So this is what we call the identity matrix. So what if I do 2 times that identity matrix? Then I would have 2 times every one of these values. And when I do that, I would end up with a 2002. Is that the same thing as just I? No. So this is not true. That's not true. You can scale geometric figures using scalar multiplication. The answer to this is yes. Yes. What do I mean by that? All right, well, let's look here. Let's see if I have some triangle. That's a geometric figure, right? If I have a triangle, I have a geometric figure. And I'm going to say, what if this is at 2, 0? This is at, I don't even know. I'm going to make up some numbers. 3, -2, and this is going to be at 1, -1. I made up some numbers. Here's what this is saying, is that I can multiply these values by some number, which means I have to do to each one of them. These values, this isn't a matrix, but I could put them in as a matrix. So how can I do that? Well, if I write these as a matrix, this is my point 1. So if I say that, or my point A, let's do B and C. So A, B, and C. This is my coordinate X and Y, and I line them up. This would be 1, -1. This would be 2, 0, and C would be 3, -2. So I can write them as a matrix. I can coordinate them all as a matrix, and I can multiply these values by a scalar. And as I do that, if I multiply it by a value of 3, then this triangle would be 3 times this original size. It would grow by that value of 3. If I multiplied it by 1/2, then it would shrink by that value of 1/2. And when I distribute this through, that would give me my new points. So that's what's happening when I talk about this geometric figures there. Scalar multiplication is a shortcut for a repeated addition of the same matrix. Yeah, so when I say 2 times this, that's the same thing as saying 3, 2, -1 plus 3, 2, -1. And if I added these together, because there's 2 of them, if this was a 5, then I would have to have 5 of them. Then I would end up with the same thing here. So it is a shortcut for repeated addition. Scalar multiplication is not possible for matrices that are not square. This example right here is not square, and we were able to do it. So that shows it's wrong right there, that this is not true. It does not have to be square to be able to use the multiplication. Any questions going through those? Kind of like these problems because it touches bases on a lot of different things. All right. Okay, so this next one says, which products can be found by matrix multiplication? Now remember, if we're going to multiply something, then they have to have the inner numbers have to be the same. The outer numbers give us the new dimensions, right? So let's look at AB. So my matrix A, let's write the dimensions for all these first so you know where I'm getting them from. So this is going to be a 2 by 1. This is going to be a 1 by 2. So remember, row, columns, row, columns. This is going to be a 2 by 3. This one's going to be a 2 by 2. This one's going to be a 3 by 2. And this one's going to be a 3 by 3. Okay, so when I go to answer these are where I'm getting the values from. Order matters. So A is first, so I need to write the dimensions of A first, which is 2 by 1. My B is a 2 by 2. So I look here, are my inner dimensions the same? And the answer is no. So I cannot multiply them. Cannot multiply them. I go to the next one, B times A. So B was a 2 by 2. A was a 2 by 1. Are the inner dimensions the same? They are the same, so I can multiply them. Check. So I just need to go through my list and do all of them. So my next one, C was a 1 by 2, and B was my 2 by 2. So are the inner dimensions the same? Yes. These are the same, so check. So I can multiply them. My next one, C is my 1 by 2. D was my 3 by 2. Are these inner dimensions the same? The answer is no. So I cannot multiply them. My D, C. So D was my 3 by 2. C was my 1 by 2. Are my inner values the same here? The answer is no. So I cannot multiply them. Then I go to DE. So D was a 3 by 2. In this case, my E is a 2 by 2. Are the inner values the same? The answer is yes. I can multiply them then. Done. EF. So E is a, E was a 2 by 3. F is a 3 by 3. So can I multiply them? My inner numbers are the same. So the answer is yes. And just a reminder that this outer number here, it gives us our dimensions. So the new dimensions, if we multiplied them, would be a 2 by 3. That's what these values, these outer ones give us. So the inner ones let us know if they're the same, we can multiply. And if we can multiply them, then the new dimensions, when we multiply them, will be those outer values, so 2 by 3. Questions? I have a Christmas coffee cup with my St. Patty's, of course, right? Okay. So flipping my page over. There we go. So this would be a geometric shape, this rectangle. Okay, so this one says, multiply the matrix representing the vertices of the rectangle to transform the figure. So it says, what are the coordinates of the resulting figure? So what is the new coordinates going to be? Well, let's look at this. I'm going to take, once you to multiply these, remember I take the rows of the first one and I multiply it by the columns of the second one. Let me grab some more colors here. Okay, so when I look at this, and let me just kind of look at what are my matrices. So I'm multiplying a 2 by 2 to a 2 by 4. So since these are the same, we can multiply, right? These are the same, so I can multiply. This looks a little blurry, so let me just kind of clean that up, see if it gets a little bit better. Then the new matrix is going to be a 2 by 4. So my solution is going to be a 2 by 4. My solution is going to be a 2 by 4. And I want to note that these values here, each of these are the points that are on here. That's where these came from. So this was my first point. So if I want to label them A, B, C, and D, just to help you guys, this was my point A, B. Oh, did I do them in order? Nope. This is my point A. Let's go this way. B, C, D. So this is my point A, B, C, D. That's probably better. And so when I look at this, then this is my X value, that's my Y value. So the top row here are my X values and my Y values. So you can kind of see how they're correlated, how we put them off of the graph into a matrix format. That's going to be important for when we look at the solution. So let's go ahead and let's multiply these. So I'm going to go ahead and I'm going to take my row 1, column 1 values. So this is going to be 1 times 0 plus my 0 times 0. Obviously, it's not necessary to even write those if you wanted to skip it, but I just want to keep you guys into the seeing how the multiplication works. So I'm going to write everything down for now. So my next one is going to be then same row, next column. So it's the next column spot. So this is going to be 1 times my 4 plus 0 times my 0. Then my next one is going to be same row, but third column. So it's going to be 1 times my 4 plus 0 times my other 4 here. And then my last one is going to be same row, last column. So it's going to be 1 times my 0 plus it's going to be 0 times my 2. So you can see where all those values came from. So notice the blue, those are the same numbers all the way across the first row. Then I go to my second row here, and I'm going to multiply times each one of these. So this is going to be 0 times my 0 there, plus -1 times my 0. My next one, it's going to be same row, next column. So it's going to be 0 times my 4 plus -1 times my 0. Then the next one, same thing, same row, it's going to be 0. And now we move to the next column. So 0, 4. And then it's going to be plus a -1 times my other And then my last one, so second row, last column is going to be 0 times my times 0. 0 times 0, and then it's going to be plus my -1 times my 2. So you could see the patterns here that the pink is going all the way across, that the rows are going all the way across. The columns, you can notice the same colors are going down. So there's a correlation. That's always the case. That's always going to be the case. Then my last step would be just to clean it up. So when I clean it up, I could clean it up right here. I could see anything that's going to be a 0. So this is a 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So this is just going to be 0, 0, a 4. This is, oh, there's a 0 right there too. So that's a 0. This is going to be a 4. This is going to be, oh, that's another 0. A lot of zeros, huh? This is going to be a -4, and this is a -2. So I kind of simplified right there. So then when I write my final answer, it's just going to be 0, 4, 4, 0. And then I have 0, 0, -4, -2. Okay. But then it says, that's my matrix, but then it says, what are the coordinates of the resulting figure? So if I multiply it by, if I take my rectangle and I multiply it by these values, what is the new coordinates going to be? Well, remember, each of these were the coordinates. So the coordinates would be these values, these values, these values, and these values. These are my X and Y values. So my coordinates would be at 0, 0. My next one would be at 4, 0. My next one would be at 4, -4. Oh, is that right? Oh yeah, that is right. And my last one's going to be at 0, -2. That's 0, -2. This is the answer they're looking for right up here. So see the box right here. So that's going to be our answer. So in other words, this point, I would have 4, -4, this point, and 4, 0, -2. So this would be the new figure. This would be the location of the new figure. It's reflected, hence why you have that negative value. It's a reflection there over your x-axis. So you can see how you could transform the figures by using your matrix multiplication. Questions on that? Questions on multiplying? Again, sometimes a visual of the colors helps you guys to see the patterns in regards to multiplying. And my last one, this is an easy peasy one because it says, given that I is equal to A times the identity matrix is equal to A, very similarly, I times A would be equal to A. It doesn't matter. It's commutative there. If A is a 3 by 3, so identity has to be a square matrix. So let me just kind of reminders. Your identity, that's what the I stands for, must be square. So the identity matrix is always square. So in this case, if we're talking at 3 by 3, it says, what is the identity matrix? Well, I already told you it has to be square. This isn't square and that's not square. Here's the other thing, remember about our identity matrix. If it's a 3 by 3, then my diagonal going across has to be my values of 1. So it's a 1, 1, 1. Everything else then in my identity matrix are going to be 0. So there's going to be a 0 here, 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 and here. Because there's got to be 3 going across and 3 going down. So the correct solution would be this one right here. And we're done for the day. I have quiz questions for tomorrow. Do I have any questions before you guys go? All right, if not, you guys have a wonderful St. Patty's Day. I'll see you guys later. Take care. Bye. You're welcome.